Bonjour, my name is José Scheinkman, and I first want to start by apologizing. Unfortunately, a family situation made it impossible for me to go to Paris. In reality, I'm today in Gray, Manhattan. The background, which is from Rio, the city where I was born, is just there because I find it nice. So I want to start by thanking Jean-Philippe for inviting me to this conference that honors Phil Anderson. I first met Phil in Santa Fe, New Mexico, when he and Ken Arrow invited a group of then much younger economists and physicists to meet at the Santa Fe Institute to discuss whether some of the methods that have been developed by physicists could help economists tackle some of the problems they were interested in. I remember Phil gave one of the first lectures, maybe the first, maybe the second, I don't remember very well. But in any case, I very much remember that during that talk, he discussed the dynamics of sand piles. And that discussion made a big impression on me. And throughout my career, I used several times ideas that I started thinking about during that lecture in my own research in economic dynamics. And today is another example of this. So I'll start by sharing my screen. And the paper I'll talk today is titled Avalanches of Price Changes. And the work was done together with Makoto Nirei, who is a professor at the University of Tokyo. And but in one of our papers, we're also joined by Laura Leal, who was then a student at Princeton, and Harris Mateen, who is now a student at Columbia. Now, I first talk about the idea of sticky prices and menu cost. Price charged by firms don't seem to react immediately to changes in conditions that imply changes in the optimal price. This is an observation which is quite uncontroversial. And economists use this idea, for instance, because under this condition, think about this idea, because under this condition, we get real effects of monetary policy, for instance. But that's not the only reason that sticky prices are used, models of sticky prices are used. But to justify the price stickiness, economists often assume the presence of fixed costs of adjusting prices. We refer to those as menu costs, but of course they can encompass a lot of different phenomena, including the fact that your customers are going to be upset with you. Now, in the presence of inflation, menu costs, we can make two observations. First, that firms, when adjusting prices, choose a higher price than the profit maximizing price. That's because they expect that prices will go down, real price will go down caused by inflation, and at the same time, it's too expensive because of menu costs to adjust the prices very often. On the other hand, they're going to wait to adjust again only when the price is sufficiently far from the optimal price for the same reason. So these distortions on relative prices make the economy less efficient. Another observation is that during periods or countries with higher inflation, inflation rates exhibit more volatility. Okay, so that's the second observation. Now, so what am I going to do today? I'm going to present a standard model with continuous firms. And I'm going to show that this model does not generate volatility of inflation. Now, then I'll think of a model with a finite number n of producers, each of size 1/n, so keep constant the size of the economy, where producers behave as if they live in a world with a continuum. That's what I call the mean field approximation. Now, what I'll show is that these models, even as n goes to infinity, we're going to obtain very different behavior. For this reason, they could be thought of less is more. because of the granular interactions that prevail even in the limit. That's the idea that I got from Phil in Santa Fe. And we're going to characterize distribution of the number of firms that adjust prices simultaneously. I'm going to call those avalanches. Sn goes to infinity. Okay, so this distribution of avalanches is going to be shown to be severely over-dispersed. The variance is much larger than the mean. And that's going to contrast with the fact that in continuous firms model, variance divided by mean should be 0. And finally, I will show that predicted distribution from the model is close to the empirical distribution that you observe in the billion price data. That's data on daily online prices in the US, Argentina, Brazil, Chile, and Colombia supermarkets, and on US department stores. So let me start just exposing the state-dependent pricing model and justifying some results without, of course, doing any of the calculations which are necessary. So we're going to think of a government that creates money at a constant rate, pi bigger than 0, and a continuum of firms that produce distinct intermediate goods. They only use labor as input. Those intermediate goods combine symmetrically to produce single final consumption good. What I mean by symmetrically is that the particular label only matters for whatever the firm is doing, the price they're charging, but all the goods come in symmetrically in production of this final good. Now, this final good is produced with constant returns by competitive firms, which means that sector is going to generate 0 profits, and also the price of the good is going to simply reflect the costs. Okay, so the intermediate goods are imperfect substitutes in the production of the final good. So the intermediate good producers have a way of generating profits. That's what we economists call monopolistic competition. And these firms, of course, maximize discounted profits. That's fairly standard, but they face a fixed cost of adjusting price. So if they want to adjust price, they have to pay a cost. Okay. Now, there's also shocks which are idiosyncratic to the firm, so they need independent across firms that are given by are derived from a Poisson process that lower the cost of price adjustment to 0, and the rate of those shocks is mu. Now, the way to think about that is that once in a while a firm gets a free price change. Okay, these shocks are named by economists Calvo shocks because Guillermo Calvo was the first economist that ever used this idea in an economic model. Okay, now the consumers receive the profits that these monopolistic competitive firms generate, they all own it equally, and also the wages that these monopolistic competitive firms pay for labor. Okay, now the consumers like consumption, and they don't like to work. They prefer leisure. On the other hand, they also have a taste for real money balances. What I mean by this is that their nominal money holdings divided by the price level, which is given by the price of the final good. That's the only thing that they consume. Okay, and this assumption is needed to generate a demand for money. There are other ways of generating a demand for money, but they all give us the same story. Okay, now, when thinking about the goods which are produced, intermediate goods produced, it's important to think not of the absolute price they are charging, which you call capital PI time T, but the relative price relative to the final consumption good, because the price of the final consumption good is kind of a price level. Okay, so we're going to examine stationary equilibrium, where the price of final goods grow at a rate pi, all the physical quantities stay constant, and the real wage, that is the wage deflated by the price of the final consumption goods, also stays constant. Okay, so in this stationary equilibrium with pi positive, firms are going to choose their strategies, their dynamic strategies. The dynamic strategies are going to be symmetric, and they all going to have an absorbing set, P lower bar, P star. So every firm is only going to charge a price in the stationary equilibrium greater than P lower bar and less than equal than P star. What firms do, if they have a price less than P bar, okay, they just immediately raise it to P star. So no price less than P lower bar is going to appear in the stationary equilibrium. If they are in between, they do nothing, and so the price is going to drift down with inflation. Because remember, the inflation is going to affect the price of the final good, and so they're going to drift down with inflation. But they do nothing, while they are in that absorbing set, unless they get a counter shock. Then the firm's immediately going to move to P star, okay, because that's a free price change. Otherwise, if they're above P star, they're going to, but not too far from P star, they wait for prices to drift to P star, for their own price to drift to P star. If they're very far, they immediately move to P star. The distribution of prices has a density, okay? And symmetry, again, the same symmetry implies that if menu costs did not exist, all firms will charge just a single price P hat. They immediately adjust the prices, force the price, constrain the price to keep it P hat. That, of course, would mean that they have to adjust their own price at the same rate of inflation all the time. And P hat is between P lower bar and P star. Now, one mathematical trick and also expository trick that adds is the following. Instead of thinking of the price that a firm charges relative to the price of the final good, which is this lowercase PIT, we're going to think of a number SIT, which is going to be in 0, 1, by renormalizing the price by taking into account the length of the interval P lower bar P star, and also where PIT is relative to the bottom point P lower bar. Now, this SIT is also going to have a stationary distribution G, and of course the distribution G is going to characterize the relative price distortions that this economy is going to face. Now, finally, you can think about how many firms pay menu costs. Those are the firms that reach P lower bar and then they decide to pay menu costs and bring back to P star. Okay. So these firms, if you want to characterize the number of firms, they are constant. And this constant depends on 3 terms. The first term is mu, which is the rate at which counter shocks are happening. Because the more counter shocks happen, the more the price level is going to be, other firms are going to be raising their prices. And that means that they can also raise their price, more advantageous to raise their prices. The second term is what is the average effect that a firm in position S that receives a counter shock has on inducing other firms to pay menu costs. That's that term, expected value theta naught of S. So theta naught of S is the effect of the firm in position S that receives a counter shock has on inducing other firms to pay menu costs, and that is average over the distribution of S's, that distribution little g. And the theta, finally the term theta that appears as a 1 over 1 minus theta, which is the effect of the firm that pays menu costs has in inducing other firms to pay menu costs. So theta acts at what economists call multiplier, and so the effect of theta appears as 1 over 1 minus theta. It is important to remember that in this model, there is no volatility of inflation. Okay? So what economists do is they add aggregate shocks. Now, aggregate shocks do exist. Obviously, anybody who witnessed what happened after COVID, the appearance of COVID, that's really an aggregate shock, or the war in Ukraine. So right now, we have a lot of aggregate shocks, important aggregate shocks that happen. But it's unlikely that they happen at the high frequency that we're talking about here. And because inflation is volatile, even at a relatively high frequency. So it's usually aggregate shocks is often a clutch that economists use to explain things that cannot be explained by the models. So the calibration, and we'll discuss that later, using parameter estimate for the US economy lead to a theta close to 0.8. Okay, so you have an idea that you divide, we have 0.2, that is, you multiply by 5 in this calculation of length. Okay. Now we come to find an n, what I call less is more. So what happens if the number of firms n is less than infinity, and you normalize it so that as n goes to infinity, all relevant parameters converge to the corresponding parameters in the continuum model. That's, as I said, an idea that I learned first from the lecture of Phil Anderson, thought about first in the lecture of Phil Anderson. So each firm now has size 1 over n, but I'm going to assume that firms choose prices if they were in the stationary equilibrium with the continuum of firms, a mean, what we call a mean field approximation. The reason we do that is that the problem that the firm faces when there are n firms, it depends on the whole distribution of what the other n firms are choosing and so on, is a very difficult problem, even to find a solution by computation, you know. And I don't think that firms have that much information about the world when they're trying to make their own decisions. Now I'm going to show you what happens in this model and how an avalanche happens, okay? So think about a world, right now we're a stationary distribution. So S is distributed station, according to a sample. We have n firms which are sampled from the stationary distribution. And here's the way I'm going to do it. I'm going to choose one firm, according to the distribution U of S, to receive the menu costs. And after that, I'm going to draw another n-1 firms independently using the distribution G of S. So it's from the copies of the n-1 copies of G of S you draw. Now, let's think about what happens. So first of all, S1 decides, he receives a menu shock, it decides to change its prices, it moves all the way to 1, because remember, S moving all the way to 1 means choosing the price P star, or the nominal price P star divided by the current price level P. Okay, so the nominal price P star divided by the current price level P gives you your relative price which you move to P lower star, and P lower star corresponds to being an S at position 1. Okay, now what it does is that raises the aggregate price level, because remember the producers of the final good don't make any profit, so they have to charge whatever their costs are. Okay, and then all the other firms, because the price level went up, are going to have their S moved by a quantity epsilon naught. It's the same for all the other firms. When you do that, you think about some of those firms, because they were close enough, less than epsilon naught from the zero boundary, are going to move negative. They never do that. They adjust their price back to P star. So that defines M naught N, and lowercase m naught n is just the cardinality of the set. How many firms adjust the prices because there was this firm that got a menu cost shock and adjusted its prices? So these firms adjust their prices, and now other firms, which are not the first firm, are not in the first set of firms that moved, are going to look and say, well, all those firms moved. That causes an effect, zeta 1, in my own relative prices, so my own S decreases, and now I think, given this change, is my initial position less than equal to the initial change epsilon naught plus the change zeta 1n. If that's true, then I now want to adjust my price. I'm going to pay menu costs, and the number of firms that pay menu costs depend, of course, on the distribution that I sampled. So that's a random variable for sure. So it's m naught n is also another random variable. And also the total number of firms, little n. So those are two parameters that would depend on. So that process continues. When did it stop? It stops when I reach around when the number of firms that change price is 0, because after that, no other firm is going to change because there's no increase in the sum of epsilon naught plus sigma 1n plus zeta 1n plus zeta 2n, etc. And then it stops. And the size of the average is simply the sum for all u greater than or equal to 0 of this variable, this random variable mun. Okay. And so that's what happens here. So in this picture, you have this first firm that moves because of the menu cost firm move. Then you have another firm, you have 10 firms here that move, but the picture will be impossible to see because of the menu costs. Firm move plus the firms plus the first firm moved. And now they cause an effect, and there's no other firm caught up here. So there's no more movement. Okay. So in fact, this other firm already never going to pay menu costs at this round. And that's what's happening in the picture. Okay. So you have to think about the distribution of mun, and it's easy to show that conditional on m0n until mun, mu plus 1n is a binomial that has to do the sampling of the distribution, right? And it's going to satisfy that as I take n to be bigger, going to infinity, the expected value of mu plus 1n conditional on all the previous m and u, okay, from 0 to u, minus theta times mun is equal to 0. So that theta from the continuum model is the same theta as the continuum model, x as a reproduction number, okay? You got, if firms have moved and causing an avalanche of up to the round u, okay, the next round is going to have an expected value, just theta times the last round. Okay, and now you sum them up and get an avalanche. Now we know that properly normalized binomials always converge to a Poisson as n goes to infinity. So this suggests that if I fix S1, that is, I fix the first firm, okay, the one that got the menu cost shock, that can change without paying a menu cost, the limit as n goes to infinity of Ln should be the sum of an infinite number of random variables mu, so that nu is a branching process where the number of children per parent is Poisson with rate theta. Okay, and m naught, of course, is going to be a Poisson with rate theta naught of S1, which is the number of firms that are going to be that would be adjusting their pay menu cost, given that a firm at S1 moved their price. Now, of course, that's all limited by the n. That's why it's only on the limit that goes as n goes to infinity, but that's to be expected. Okay, and you actually can prove that, and we can think about what that limit is. So, conditional on the Calvo hit at a point S, okay, the limit distribution capital L has the following probability, is the following probability distribution. The probability that L equal to L is given by the right-hand side here of equation 1. This is what's called in statistics a generalized Poisson distribution. Okay, and I want to use two properties of the generalized Poisson distribution. First, that the expected value of L condition S is that theta naught of S divided by 1 minus theta. But the variance is theta naught of S divided by 1 minus theta cubed. Now notice the following: what statisticians call the coefficient of variation, that is the variance divided by mean, is independent of S. Okay? And it's exactly 1 divided by 1 minus theta in parentheses squared. Okay, now the tail of that distribution is like a dampened power law, okay, with a particular exponent 1.5. So it's dampened because of that whenever theta is less than 1. As theta converges to 1, the tail of that distribution is actually just a power law. We know that theta is always strictly less than 1, so you're never going to get to the power law, but you can get pretty close to a power. Now, if you don't condition, you get essentially similar results. You don't get exactly a generalized Poisson distribution. You get some distribution in the class, what's called Lagrangian distributions, but that's not a problem. You can still compute the expected value and the variance. The variance is going to reflect the fact that S varies. There's some randomness according to the S. But in any case, you can prove that the index of dispersion, again, or this coefficient of variation, varies by mean, is the same thing. It varies by mean, sometimes called the index of dispersion, sometimes coefficient of variation, is going to be greater or equal than 1 over 1 minus theta squared. Okay. Now, we're going to look at simulations of the model. You can simulate the model for very large n. In particular, you simulate for n equal 40,000. This number 40,000 comes from calibrating to the literature. And inflation rate is equal to 3%, which was the average inflation rate of the US for a long time. Now, of course, it's much higher. It had a long period which was much lower. But that was the average inflation rate for a long time. And you can kind of simulate the model, but simulate the histories of the model. I'm not trying to simulate samples for an IID because, you want to look at the whole history of the model. Now, if you do that, the blue dots represents our simulation of the model. Okay. And the red means the closest generalized Poisson that you could fit. Now, there's something very interesting. We're especially interested in the data. The closest generalized Poisson that you can fit has a theta which is larger than the one you use for the simulation. You don't like to understand that. While the simulation you get 0.72, where the simulated L was simulated with a parameter theta equal 0.72, the histories, actually generate a generalized Poisson which has a higher theta. Okay. Of course, the one that really interests us is the one from the histories. Okay, we don't observe constant samples from a stationary distribution. We start maybe at a stationary distribution, get a sample, then another firm gets the model runs for a while with no changes in prices. Then another firm gets a manual cost shock, so we can charge equal to 0. But now you're no longer the stationary distribution. You do the same process again, and you're not going to get exactly the one predicted. But in any case, you get something that looks like a generalized Poisson, except with different parameters, and in particular with a higher theta. So we get this higher number, it's 0.91 instead of 0.73. And we can see that this larger theta hat in history actually results from fluctuation and distribution of firms' relative prices, which is the history really matters, okay? The other point you have to think is that if you're going to apply it to real-world data, you have to aggregate. You're not going to observe every second what's going on, okay? So we do a simulation with the aggregation at daily level, and we get a theta which is very close, a theta hat estimate, which is very close what you get with a simulation where you can observe every instant, okay? So it is true that in that case, the GDP fits well for days where total avalanches above the median, but in days with very small number of total reprices, the Calvo shocks are causing a large fraction of total price changes. Remember, we can't observe Calvo shocks. All we can observe is an avalanche, okay, and that occur in a day. And we don't know if that avalanche was a result of a single Calvo shock and one avalanche, or two Calvo shocks and two avalanches. We can't identify that from real life data. Okay. Now, we're going to spend the last 5 minutes or so discussing the billion price project, but I can't not thank Jean-Philippe Bouchaud, because I gave a theoretical talk on part of this material that I have now on a seminar at Polytechnique, the CFM chair seminar. And during that seminar, at the end of that seminar, Jean-Philippe suggested you should look at the Billion Price Project because they have a lot of data on price changes. They have online price changes daily. Okay. And so that's what I did. And Makoto and I and our colleagues did. That's more precise. And we look at avalanche of positive repricing because the model to adapt to negative repricing has to be more complicated. We have done that by introducing productivity shocks to firm against, again, idiosyncratic. So I'm not discussing that here today. And look at products. They all have at least 100 days of observation. And we use an algorithm because we're interested in price adjustment that does not count price increases after sale. So if a firm puts a certain item for sale for a week and then goes back to the normal price, we're not going to count that as price increase. So here's a data overview. You see that the observation for every data set is around 13 million observations, except the Colombian data set has about 5 million only. But the number of unique products, about 20,000+, an average 25,000 unique products. For Colombia, you only get about 10,000. That's a normal, it's a smaller data set. But the ratio of observations to unique products is more or less the same. So we get about 500 days of observations in each data set. There are negative price changes, I said. Now, if you try to affect data, we have two ways. We can either use a moment estimator or nonlinear least squares. Nonlinear least squares fit better, but the data are very close. Here there's the fit that shows better. But in fact, if you look at the data, the data are very close. They're all around 0.9, just like in our simulations. Okay. Now, here's the counter cumulative fit. So in the horizontal axis, I have the size of an avalanche, okay, in logs, okay, and of course, we threw out days which there's no price changes, but there's a day there's a price change. You just measure how many price changes happen in that day. We don't know if it was one avalanche or several avalanches, but that's a limitation of the daily data set. And on the vertical axis, I have the counter cumulative distribution, also in logs. And you see that it all fits pretty well. The fit is less good for Brazil than for the US data sets. And it's better for Argentina than for Chile. Maybe it's actually better for Colombia than for Argentina or Chile, but they're all pretty good. And the data is all pretty close, around 0.9. So that's kind of surprising because, as I said, we didn't develop the model looking at that set of observations. Jean-Philippe was the one who told us about the set of observations we could test. So it's really out of sample testing. So what did we show today? First of all, that a state-dependent pricing model with a finite large number of firms, in our case 40,000, generates repricing avalanches of stochastic size and inflation fluctuation from idiosyncratic shocks. Inflation fluctuates because inflation only happens when an avalanche happens. Okay, and over the year, if you look at it at a year, 6 months, you're gonna get fluctuation on the rate of inflation. Okay, even though the governments are aiming at 3%. The fluctuation of avalanche size is related to the multiplier theta that results from complementarity of price changes. We produce a precise distribution of the limit distribution of the avalanches, and that has a coefficient of dispersion of repricing avalanches bounded below by 1/1 minus theta squared. The calibration using US data showed theta close to 1 for 3% inflation. And the calibrated model can generate a relationship, I didn't show that to you, between inflation level and volatility close to the one observed in the US. Now, GDP fits well, repricing avalanches, the generalized Poisson distribution fits well, but generates a theta hat larger than the one you use to generate the data. And that has to do with the dynamics, because the dynamics make the sample, the distribution of firms over time to diverge from the stationary distribution. Now, we know that comes from that because we did use subsamples to test for that, but we don't really understand why is it that this deviation from the stationary distribution always increase the data head. It's probably related to some form of self-organization that we don't completely understand. Okay. We've also showed that data is close to 1 for the data set for the billion price project. We show the distribution of the number of daily positive repricing is well fitted by a generalized Poisson distribution. And I think the strategy of choosing a model with a finite n in which agents use mean field policy functions is probably applicable to other problems in economic dynamics. I thank you very much. And again, I'm sorry for not being with you guys. Goodbye.